Good. So we'll talk now about Hadoop, which is the open source version of MapReduce, and it's the topic as well of today's lab. So what is Hadoop? Hadoop is the name of this elephant here, but it's also the name of an open source distributed processing framework based on MapReduce. Effectively, the people of the Hadoop project took the white paper about MapReduce and implemented the ideas in a Java open source project, an Apache project. So in terms of some of the naming, we have what's called a name node on the Hdfs side, which is somehow the master. And here we have the chunk servers in GFS, or we call them data nodes in Hdfs. Something similar in Hadoop, we have a job tracker that's sort of like the master that controls the work that's going on among the machines that are doing the difficult work, let's say, of partitioning the data, sorting the mapping, partitioning, sorting, reducing, and so forth the data. So some reference material for the lab. This is mainly just things that you can refer to, but I would like to give a brief kind of introduction to how you build things with Hadoop, right? So the first thing is Hdfs. So your input and output when you use Hadoop will typically be a distributed file system, the Hadoop distributed file system. So when we have everything installed on the server. So when you log into the server, you can use Hdfs space DFS, distributed file system, to get a list of commands that you can call on the distributed file system. And you'll see some of those commands will be familiar to people who know a little bit about Unix or Linux terminals. So we have ls to see what all the directories or files are. We can make directories with makedir and so forth. So we can see the commands and their arguments. So we would type, for example, hdfs dfs space dash, let's say copy to CP to copy a file from a source to a destination. So we can also access data from Hdfs programmatically. And here's an example in Java, where what we're doing essentially is we're opening a default configuration, which essentially tells us where it allows us to pass
el laboratorio ahora. Están explicando el laboratorio.
Hdfs.
¿Cuánto fue?
We can check to see if a file exists. If so,
Ya,
we're
una
going to
empanada
delete
vegana.
it.
Gracias.
I just realized I can't hear you, so I see there's lots of messages,
Gracias.
but I can't hear you. Let me check. Sorry. What's going on? Speakers. Okay. Share screen again. Okay. Now I've lost the chat. Okay, I'll continue. So we can check to see if a file exists, and if so, we delete the file. Otherwise, we can, for example, create a file. We can write some message to that file and close the file. Okay. We can also here have some example of how to open a file in Hdfs and read it, print a message, and then close it, right? So here you have commands to see if files exist, to delete files, open them, write to them, open them, read from them, close them, and so forth. So in general, we won't need to do this because Hadoop will do this automatically. But if we wanted to open a file on Hdfs as if it were a file on our hard drive, we could do something similar, but using slightly different classes and commands. Okay, so there are different formats of input. The one we'll typically use will just be text input. Okay, and this is the default one. So this just reads line from the file. So when we read input in particular into Hadoop, the key will be the offset of the line, like what position in terms of bytes we are into the file, right? In general, we won't use this, we'll just ignore it. the value will be the line itself. So when we're reading the input, will be passed key value pairs. The key will often ignore, but if we need it, it's the byte offset of the line that we're reading, and the value will be each line of the file. So essentially, we can read a file on HDFS line by line. There's also a key value input format that allows you to read in custom key value pairs. So the key will be everything up to the first tab character, and the value will be the remainder of the line. And finally, we have a binary format that we can use that's sometimes used internally, that's more efficient than these other formats, but more difficult to read. So we need to use special commands to read them from HDFS, for example. So it's a binary format, a compressed format. And we can define what types of keys and what types of values we have. So in general, we'll use text input format. It's the easiest. It's maybe not so performant as sequence file input, but we can read it more easily from the client. We can see what's in the file. Okay, so we have a map where this is just some hypothetical task where we want to count some number of citations. So this is how we implement the map function. So we need to have a class called mapper, and we need to pass it 4 different generics, 4 different types. So the first type we don't care about, it's the offset of the file. It's the input key. And this is the input value. This will refer to a line of the file. So we use text. Next, we have an output key and an output value. So we have our output key will be a citation, some word or some string, and we're going to output a 1, like we saw before in the class, where if we count things, what's typical is to write the keys of the things we want to count and the values as 1 in the map. And later we'll sum all of the ones. So, okay, so we create some objects here, so we don't have to create lots and lots of new objects. And this is sort of a pattern they use in Hadoop. I don't know if it really helps all that much, but one thing that's interesting is why are we using text and why not string? So the objects that we pass in as arguments to maps and that we write out must implement some special functions. In particular, they must have a special serialization, and we can also override certain things, like to change the order of those, to change how they're partitioned, which I'll talk about in a minute. So we don't just pass plain strings here, but we rather pass objects that are from the Hadoop library. So we have text, int writable, long writable, these sorts of wrapper classes, right? That just take as an argument. You can construct the strings or the normal Java objects with them. So we have our map object here, which has our key, our text value, and our context. So this key here, again, comes from the input. It's the offset of the file. In general, we don't care about it. We don't use it. It would be a long writable, but we don't care about it. So we just say object, okay, whatever it is. Here we have the value, which will be a line of the file. So essentially, the MapReduce framework will open the file, and for each line of the file, it will pass that line in here to map. Okay. Then we have context, which is our way of referencing the Hadoop framework. So this offers us an interface to the Hadoop framework. So we're going to read the string from the value, from the line of the file. So this is just a line of the input file. And then we're going to split the file. We're going to parse the line to get whatever data we want from it. And then we're going to, for example, we're going to set the title of the paper in, this would be the first element. This is the thing we want to count. And then we output that thing we want to count with the number 1. Okay. So this is overall the map. So the tricky things here, the common problems are in these generics, but Java will tell you if there's a problem, which is nice. So this is the input key. Generally, we don't care about it. It's a long writable, but here we can say object. We have the input value, which is a line of the file, which will be text. Then we have to choose our output key and our output value. So in the output key, in this case, we're going to use text because we want to write a paper title. And then we are going to write for each paper title a 1, right? So this will be why it's int writable here. Okay, So here's the explanation: input key type, input key value, map key type, map key value, map value type. Sorry. And we have the input, which is the file offset. We have a line of the file. We have our interface to the MapReduce framework. And here we are writing our output, the output of the map. Essentially, this will then, underneath, it will start partitioning the data and deciding which keys go to which machines and sorting them, and so forth. So this takes care somehow underneath here. We have all the things that happen after the map. So here, this handles the input for you. So you don't need the commands we saw previously. So it will automatically open the file for you, read each line, and then pass it to the map. So, okay. So this is a very typical thing to implement in MapReduce. So this is something that's essential in MapReduce, right? Your MapReduce task is always going to include at least one map. If you want to change some or create some new sort of object that you want to pass around in the Hadoop framework, you can implement writable for values. And writable, for example, we can create a custom object that describes the citation with the citing paper, the venue, and how many times that citing paper mentions citing paper, where that paper was published, and how many times it's mentioned. Okay. So we can create a custom object like this. And if we want it to be compatible with the Hadoop framework, we need to implement a few things. So we have our constructor, first of all, so that's fine. Afterwards, we have to implement a write, which tells MapReduce how to serialize the elements of the class into bytes. Then we need to have a read fields, which does the opposite. It essentially tells you how to read on the other side, the thing that you serialized with write, and parse it back into the object. So just to mention here that this should correspond in the same order to this. And finally, we have toString. So we have, some way of printing the contents of the object. In general, this is not super necessary. It's quite rare that you would have to implement your own object, but you might find it useful. You might find it convenient, or you might prefer to just create a string that maybe uses hashes or gatos or some symbols to separate these, or you could like pass a JSON string and just parse it, right? But you could also pass them as Java objects, in which case you would have to implement these. So this is what you need for values. So that we're always working with key values. So you need a writable interface if you want to implement a new type of value. So we have to implement writable. We have to write out the fields we want, and we have to read those fields back in. So these should be in the same order. Okay, if we want to use something as keys and values, okay, we need to implement writable comparable. Okay. So what does this need to add? It needs to implement all of the things of writable, so write, read fields, and so on. It also needs to implement a compare to method, and this is used for sorting. So we sort the keys. So if we want to define a new key, we need to define the comparison so that it can be used for sorting. We also need to implement the equals and hashcode methods. Hashcode is already Hashcode is implemented by default in Java objects, but we need to override both of these to make sure that they're doing what we would expect. So, okay, we have a new interface, writable comparable. We have the writable thing as before, plus we need to be able to sort keys. So we need a good implementation of compare to and equals. And the hash code is often used as the default partitioning. So we need to define a sensible hash code as well. Okay, so when we're using the keys, we need to decide what machine that key value pair will go to. We use the hash of the key to decide the machine. So we need a good implementation of hash code. So partition, Andres, you have a question?
Yeah, I wanted to know because in the first like implementation of the writing, you used a context for which I assume is the Hadoop file system, but then you use the data something on there. You have a context that as output.
Yep.
Do we have to have a specific object for the Hadoop file system to write to?
So for all of this here, let me mention that you won't have to worry about this immediately. This would be in a hypothetical context. If you wanted to read files from HDFS directly, you can do so, right? As if they were files on a almost like they were files on a normal file system, on a local file system. But if you use Hadoop as we're doing here, then Hadoop will take care of all that input stuff for you. And essentially you can jump straight into just implementing the map here, in which case you'll have your specific reference to the Hadoop infrastructure, and Hadoop underneath will have its access to HDFS, right? So when you run this, you actually call it, you don't run it directly like as a jar, as a normal jar. You actually pass it to the framework. So the framework itself takes the jar and then it understands its own references. It understands where, it's sort of like the framework itself takes the jar and runs it. It's not that you're running the jar somewhere else. So you don't need to really specify any specific configuration for the Hadoop infrastructure, because you're actually going to call the Hadoop infrastructure and give it the jar. Not sure if I answered the question.
Yeah, kind of. And then we just have to implement the specific interfaces that we want, and that's it, right?
Yeah, the most typical things you'll need to implement will just be, for one Hadoop job, will be one map, one reduce, and one main method. The other details I'm giving for completeness, if you wanted to create custom keys and custom values, you would need to do this writable and write comparable, which I'm mentioning mainly for completeness. But in the lab, you won't need to do this. You'll need to just implement a map and a reduce.
Okay, thank you.
Okay. So if in some future scenario you wanted to implement custom types, custom key types, custom value types, this is what you'd need to do. Okay. So the partition, you don't have to do anything. You don't, and by default, it will use a hash on the key and then do the modulo, the number of the machines, and the master will figure out the best number of machines to use and so forth. If you wanted to, you could override the partitioning. So you could define a custom partitioner, in which case you would need to implement something like this. So you implement a partitioner and you say what kinds of things you're partitioning. What are your keys? What are your value types? In general, you shouldn't use the values for partitioning, but you can if you want. It would be kind of an anti-pattern. It's something you wouldn't do normally in Hadoop, but you can. So you have your get partition here, and then you basically pass the key, the value, and the number of machines, and then you have to output an ID for the machines. So what we're doing here is actually we're re-implementing the default partitioning. Okay, so we implement the partitioner interface here. And here we implement this method. And so what we're doing is just re-implementing the default partition here. Okay, so we have nothing to do here. All is good with shuffle. I can see the chat now, cool. And the tab character is /t. Yeah, exactly, yeah. So tab separated values is much better than comma separated values, as I think everybody knows. If not, we can have a flame war about it, but I much rather tab separated values than comma separated values, and so does Hadoop. Okay, so then we have shuffle, and this is the framework will do all this for you. You don't have to do any of this. If you wanted to, again, you could implement your default keys, which will be used for sorting. So the sort comparison is completely automatic as well. We don't have to do anything. But if we wanted to change the sort order, we could implement a custom key, and we could change our compare to method here, right? So this is how, if we wanted to do, we wanted Hadoop to process things in an inverse order, we could do it that way too. So here would be what affects the actual comparison used for sorting, the sort order. This we have to implement, right? So apart from the map, we saw a lot of details of things we could tweak or implement ourselves, but typically you will go map and then you will implement your reduce. So your reduce here has to extend the reducer class, and we have to pass 4 generics similar to the map. So we need to pass the input key for the reducer and the input values for the reducer and the output keys of the reducer and the output values of the reducer. So the input key and the input value here must correspond with the map you're using. So the map we're using will output a citation and a 1. So it will be text for the citation, string, the name of the paper, and 1. And then we need to specify, we need to choose what kinds of pairs we're going to output. So since we're counting, we're going to output the title of the paper and a count, how many citations it has. So here we see the implementation. We're passed a key, and we're passed an iterator of all the values for that key that have been seen in the entire file, even if the file is split over lots and lots of different machines. We will get in this one call the key, which will be the paper title, and in this case, a list of ones or a list of numbers. And we again have our kind of reference to the framework, the output. So we create a 0, we iterate over all of the values, and we sum them, right? So we just sum all of the values in this iterator. And this here is optional. This here you don't need necessarily. Oh, sorry, I have 2. It'll have no effect, 2 semicolons. But what it does is you can keep a counter, like a way of logging to say, how many papers have you processed. So we have a counter called citations, which is a map from the first letter of the title, how many papers we've seen that start with B, for example. And we're incrementing it by 1. So we're keeping account of how many papers we've seen with each particular letter, starting with each particular letter, which is a bit silly, but so this is just used for logging. It's not part of the logic of the reduce. The final part, of course, is to output the paper title and the sum as its count. Okay, so again, we have the key, we have the values, and iterate over all the values for that key, and then the context for the output. So this you will have to implement. You will see this in the lab. So the map and the reducer are the 2 most important part. And here we write we write our output as key value pairs. Again, this handles the output for you. So we saw in the first slide how to open and close and write the files. You don't need to worry about this. This here, Hadoop framework will call the Hdfs framework to write this file. Okay, so again, then if we wanted to, we could use the input or output commands that we saw in the first slide to read the output of the reduce if we wanted to. So, sorry, okay, I have this animated again. This is the same thing we saw before. So we could open the file that we created with the reduce and read it into our Java program as if it were a normal file if we want to. In terms of the output, we have the same outputs as we have inputs, right? We have a text output. We have, so the key value pair, we don't have a key value pair because by default, this text output, is compatible with the key value pair input. So it will write key tab value. So tab separated pairs. And we have a sequence file, which again is the binary efficient format. And we have a null format that just essentially it's a do write nothing. So it would be a little strange, but maybe you have a reduce that where all you're doing is maybe logging some information about the input, or you have some small value, right? So you could even use a logger for that. The most common here by far, the one we'll use in the lab will be the text output format. Okay, the last thing you'll need to implement besides the map and the reduce, if you don't have any other custom elements, will be the control flow. So you need a main method in your job that will, has a configuration. It maybe accepts some arguments from maybe the command line, for example, like to say, the command line, you might say, what's your input file, what's your output file, right? So we parse the arguments, input location and output location on Hdfs. And we have to create a new job, which is just a default configuration. We need to set the input paths and the output paths. So we're input paths in terms of which files we're going to read from, and we can read from multiple files if we like. The output path, which will be the name of the reduce, the file that will have the output of the reduce. We need to set the the keys and the values for the maps and the reduce. So this is the reduce key and value. This is the map key and value for the outputs. We have to specify a mapper. We have to specify a reducer. And optionally, in some cases, we can specify a combiner. We need to specify the class, the main class, essentially the class that contains this main. And then we can call the job and wait for it to complete. So if we set true here, the Java, this main method will not return until the program, the task is complete. So when this is launched, it will be launched, you know, not in the same process. It will be launched on the framework. So it's running independently. So in this case, we will say, okay, let's wait, like as if it were a thread. Let's wait for it to finish before we end this main method or continue in the main method. So key parts here, we need to create jobs. We need to create an input and output path. We need to set the type of the map and the types of the output keys and values for both the map and reduce. We need to set the mapper class, optionally the combiner and a reducer class. And then we need to, if we wish, we can run the job and wait for completion, run the job. And if we wish, wait for it to complete, or if we want to continue with the rest of the code, we could put false there. Typically, you want to put true because you'll get some nice logging that you can kind of follow along with. You can see what's going on with the job. Whereas if you put false, in this case, the program will just end. Okay. Any questions? I'm speaking actually in much more detail than I had intended. I wanted to just leave these as reference, but maybe it's worth going over in a little bit more detail. So if there's no questions, just a couple of other things. What happens if you have multiple inputs? In the last example, we had one input and one output. So in this case, for example, if we have multiple inputs, we can, in this case, 3 inputs, 1, 2, 3. We can create multiple mappers. So we can create multiple instances of the same mapper, or we can create different mappers for different input files. That's no problem. All we need to do is use this multiple inputs where we add the path, okay? So we add the path and then we add some the details about the mapper that we will use for that. So what's the format of the input and what's the mapper we'll use for that particular input. So we can add these 2 multiple inputs. And in this case, we'll always have one output path. Okay. So this is how we can have multiple inputs. And we can set even a different map for each. In this case, sorry, we have receipt items mapper. This is referring to the example we saw in the class. And we have a receipt times mapper. So we have 2 different mappers for two different jobs, different maps for different inputs, sorry. And we have one reducer. So you can have multiple maps. You can have 1 or more maps, but you always have one reducer in one job. Okay. You need a mapper always, even if the mapper does nothing except for print the key and value exactly as it is. You always need a mapper, because the mapper does the partitioning and the initial sorting before the partitioning. So you always need a map, but you can have multiple maps feeding into one reducer. What happens if you want to chain multiple jobs? Well, by far the easiest is just that you wait for completion here on job 1. And when it's done, you take the output of the first job and you feed it into the second job and you're done. Yeah. So essentially what's key here is to make sure that you run and you wait, because if you don't wait, you'll start a second job whose input is not ready because the output of the first job is not done. Right? So this is the easiest way to chain jobs. Or an even better way, depending on what you want to do, is just to have separate jobs and to manually call them. But if you want to do it programmatically, you can do it this way. So the output here of job 1 is just set to the input of job 2. Okay, we can set the number of reducers if we so wish. So we can say, okay, we only want to have 1 machine doing reductions. Okay, this sounds a bit weird. Why wouldn't we have like all our machines reducing? Like why don't we have all the machines summing all the 1s for different citations or summing all the 1s for different words? So the question is, why would we want to have fewer reducers? And the idea is essentially that we might have a small output from our reducer. So we might actually have, for example, some data that we actually want on one machine. So when we do, if we have n reducers, we'll have the output split over n machines. And maybe we know that the output will be quite small, and actually we just want to do all the reduction on one machine to have one simple output, one output on one machine. So counters we saw briefly. Counters are just these things here that essentially the context has a group of counters that we can use to count certain things that we're processing. And the other thing would be a distributed cache. So you say, what happens if I need to pass some data to all of the machines that they can take into account when they're doing their maps or their reduces? And in that case, there exists a distributed cache, which makes the data available locally to all nodes. Okay, so maybe, for example, if you're counting citations, but you had a blacklist of 10 papers that you were cheating somehow, that were falsifying citations, and you didn't want to count them, you could pass that in your distributed cache. But the idea is that it should be used very sparingly, rarely if ever, and it should only be used for small data volumes. So the idea in general is that you really don't want to share too much global knowledge. But if you think there's a small section of global knowledge, a small volume that can simplify your task, you can share that in a distributed cache. So in general, you won't use this, but it does exist if you want to use it. So if you're looking for more details on the internals of how Hadoop is implemented, there's some nice slides here. They're from 2014, but the overall architecture hasn't changed in the recent years. So there's lots of details there, but also it serves as a reference that you can kind of return to when you're doing the lab. So any questions?
Yeah, when we work with more than one machine, we are using a master node, but now in the lab, we are just gonna use our machines, or are we gonna work on a server?
So you're going to, it's a good question. So you're going to work on a cluster. You're going to work on the same machine as you did the RMI stuff. So that machine that you use for RMI, we'll give the instructions if you haven't seen lab 1 or lab 2, sorry. But that machine, you will log into it, and that machine happens to be the master server of a 4-machine cluster, a very modest 4-machine cluster. So I think it has maybe 6 or 8 gigabytes per machine, but you will have everything installed there. If you wanted to, you could, for example, for fast debugging or testing of your code, think about installing Hadoop locally, but that's not necessary. It's not expected. So you can use the server and implement all the labs there.
Okay, and can I work with Hadoop locally, and instead of using more than one machine, could I maybe use more than one core on the same drive?
Yep, you can.
Nice.
You can also install like Hadoop in a local mode, like for testing or for development, which in general is kind of a bit complicated. It's not so easy, so we just install everything once rather than having you all install all of this. So it's not expected, but and we'll have one lab with Hadoop. So it may or may not be worth the effort, but let me go back here. What you will need still is a job tracker and a job node, but it could develop these, run these on 2 different cores, for example. In general, as a sort of side note, we can also, it's not necessary to have each node on each machine. If we have a real cluster and we think that we can use multiple of these, we can actually have multiple job nodes running on the machines, or we can have a job tracker and a job node running, or whatever. What tends to be a limiting factor is the disk, actually. So, in general, I think they say that you shouldn't really have more than 2 job nodes per disk. So even if you had lots of CPU and lots of memory, if you have 1 or 2 disks, then that can be a limiting factor. But anyways, if this is more for efficiency, for development or whatever, there's no problem, right? So you can even, you could launch locally multiple job nodes if you wanted to do that, yeah.
Cool, thanks.
Okay. Okay, no more questions? Yeah, so let's pass to the lab. So let's pass to the Discord, stop share. And so one thing to mention maybe briefly is just that this lab is a bit longer, but this topic is very important in the course. So this lab is, it goes through quite a bit. Not all the labs will be this difficult, but it's not that the lab is difficult, it's quite long because there's quite a lot to go through. But it's a very important topic of the course. So one of the two most important topics. For that reason as well, the lab, this is the first obligatory lab. So this lab will be marked as part of the final grade. It will form part of the final grade for sure. So see you in Discord if there's no other questions. Okay.
I have a quick something quick. Well, you said that the lab that was big. How much time do you think we should dedicate to this?
It depends. I think if you're familiar with Java, I think it's not going to be, there isn't a whole lot to code, and mostly you'll be copying examples and changing some details. So I don't think it's especially if you're familiar with Java, I don't think it'll be a lot of effort. There's more effort in kind of getting to grips with the server, getting the copying the jar onto the machine and so forth, running tasks and revising the results. So I would expect somewhere around maybe 3 hours for one person doing it alone, something like that. And someone who's not maybe so expert in Java or on that, around that sort of ballpark.
Okay, thanks.
And in general, the lab should be more like 1.5 hours to 2 hours. Okay, so I've spoken more than I wanted to, apologies, but let's pass to the Discord. Let's start the Discord. One thing to briefly mention, not that it's so relevant, but I have a defense at 4 o'clock, so I'll have to leave a couple of minutes early. Apologies for that, but yep, we'll pass to the Discord. See you there. I'll leave this open just in case there's questions.